Welcome to a discussion of piano scale evaluation. I'm Mark Gallant, Opportunist Piano Service. This presentation encompasses an important preparatory step in the restringing process. We'll touch the topics of the old scale copy methods, why scale evaluation and specification should be a step in restringing an instrument, the parameters of a scale that should be scrutinized, what information is needed to produce the custom bass string set, and what measurements to take from the original scale to start the analysis. Many technicians reproduce the existing scale on an instrument. The plain wire sections are the easiest to reproduce faithfully by simply using the same wire gauge that's already on the piano. The bass strings are a little more difficult to replicate if the original equipment manufacturer scale is not available. Many string winders have a good deal of history acquired from experience or manufacturers or other archive methods to produce a very reasonable replication of the original bass strings. The paper pattern created by stretching a large sheet of butcher or brown wrapping paper over the plate while strung and rubbing to transfer the scale data still may be used. Accuracy loss could be considerable with this method. Hey, just send in the old strings. Well, not a bad solution for duplication of the scale present in the piano. Shipping costs may be an issue. And unless the old strings are shipped back with the new ones, there is no quality control. Scale duplication or replication leaves the technician with minimal knowledge or understanding of the scale at best. Results in the same issues as the original. However, without the insight evaluating the scale parametrics can give a technician, ignorance might be bliss. Why do we want to go through the hassle of collecting and evaluating the scale parameters? Because as a technician restringing an instrument, we have the opportunity to make it better. Mass production of anything demands keeping the cost of manufacturing at a minimum. In the plain wire sections of the piano, this translates to changing the wire gauge as infrequently as possible. In wrap strings, it may mean compromising some parameters, such as length of exposed core wire, long enough to accommodate all intolerance nuances in the production of the piano, and or a reusable engineering for more than one instrument model. When restringing an instrument, we can custom fit the scale to the uniqueness of the instrument. Some of the original strings were wound in materials that are just not available today. Many older instruments used a soft steel wire for string winding. The characteristics of this steel versus the copper used later and mostly by string winders today is quite significant. Replication of wrapped diameters without regard to the material change would result in a scale noticeably different in tone, volume, and tension. A silver-nickel alloy and aluminum alloys have also been used to load the bass strings. Wow, the difference between aluminum and copper is very significant. The main parameters that can be controlled during a restring are the selection of core and overall wrap diameters to influence tension, volume or impedance, and inharmonicity. Capturing and evaluating the original scale data may allow a technician to more closely replicate the characteristics of an historical instrument when a change in winding material is needed. A good evaluation tool will allow the technician to evaluate the scale at the design pitch as well as any target pitch. Manufacturability was discussed earlier. The opportunity to custom fit the mass-produced scale to the uniqueness of the instrument is presented to us when we restring the instrument. Evaluation of the scale allows the technician to smooth out the curves of several important scale characteristics. The scale evaluation tool should present these characteristics graphically to assist in the visualization of the data. These two graphs show the original scale tension in the top graph and the tension of the scale used to restring this old Steinhauer, a 1905 upright with steel-wrapped strings. The section markers in this and the following graphs depict the double-wrapped, single-wrapped, tenor, and treble sections of the scale. The comparison shows little change in the double-wrapped section in tension, but a much smaller transition from single wound to plain wire, and a considerably smoother curve eliminating the stair step of the original scale. Keep in mind the final scale must incorporate the best compromise of tension, volume, and inharmonicity. Let's look at the volume curve. The parameter of volume needs a little explanation. It is a theoretical value based on a standard hammer and a standard blow to produce a representation of relative volume based on mass and tension. It's a representation of loudness and sustain without regard to the characteristics of the soundboard or bearing or any of that. The inverse of volume is impedance, or resistance of the string to produce sound. The jump from wound to plane has been eliminated. The original scale clearly demonstrates the classic stair-step of holding the same wire gauge as long as possible as a compromise to manufacturing costs. As technicians, when we restring, it costs us very little in time or materials to change wire gauge as often as we wish. The final curve is very smooth and more closely follows an expected logarithmic curve. You may notice the graphs for volume are logarithmic. That is to say, the distance from 1 to 10 is the same as the distance from 10 to 100. If this information were displayed in a linear mode, the nuances would be lost. Inharmonicity is the result of using real materials, materials that have stiffness. The stiffness of the string results in an effective dead zone at each of the nodes of the harmonics of a given string in a given position of the scale. This dead zone is what causes the speaking length of the harmonic to be shorter than the theoretical perfect length for that harmonic, resulting in the harmonic being sharp to its ideal. Therefore, it's referred to as a partial rather than a harmonic. Whew, that was a mouthful. Inharmonicity for the purpose of scale evaluation is expressed in cents. This deviation is multiplied for each partial. For simplicity, the second partial is 2 times the inharmonicity constant. The fourth partial is sharp by 4 times that constant. The formula is more complex than that, but it's a good analogy for this discussion. So let's look at the changes here from the original. The change from steel wrap to the copper wrap is primarily responsible for the better fitting of the base section, a little smoother section across the break, and less stair-stepping. Tension, volume, and inharmonicity are calculated values produced from measurable elements of the scale. The next few slides will display how changes in these measured elements affect the calculated characteristics. The comparisons in this and the following slides were created by holding all other parameters of the string constant. This is not a resultant or final scale, just a comparison of the change in a single element and its effects. This chart shows that a change in material significantly affects all 3 parameters. Changing the speaking length by 1/8 of an inch either side of center gives a very small change in the 3 parameters we are tracking, but it's packed with good information. The small change here demonstrates the greater the accuracy of the data collection, the more precise the results will be. It also shows that a minor pin alignment may not be too serious. Tensions change only a couple of pounds, volume is hardly noticeable. The inharmonicity exhibits the greatest relational change. This data also shows that we are looking for something in the scale that is stand out from the noise before we change something. These changes, as small as they are, show us the relationship to speaking length. Increase the speaking length increases the tension and the volume, but it decreases inharmonicity. Why? More length means more mass. More mass means the tension goes up to maintain the frequency of the specific note. More mass means more energy transferred to the bridge soundboard system for more volume. Greater the length for no change in diameter means the dead zone for each partial is relatively smaller for less inharmonicity. Let's mess about with core size. Here again, the larger core, the more the mass, so it's no surprise tension and volume react the same way as with speaking length. It's probably obvious to the most casual observer that an increase in core diameter will affect the relative stiffness of the string for the given speaking length, and thereby directly increasing the inharmonicity factor. Most of the scale evaluation exercise is about the wrapped strings. It's where we have the most parameters to play with. This example has the overall wrap diameter changing by 5 mil increments. Just so we're all on the same page, a mil is 0.001 inch, 1/1000th of an inch. Core and wrap diameters are expressed in mils as whole numbers. Back to the chart. Again, messing with the mass, therefore changes are directly proportional. This time, though, both of them show some real change. Inharmonicity is inversely proportional. Why? Changing the size of the core directly affects the stiffness, but wrap is at 90 degrees, if you will, to the direction of pull, or the direction of stiffness. That's latitudinal versus longitudinal, and therefore has very little effect on the stiffness while adding mass and diameter and bulk. The difference in diameter is part of the inharmonicity calculations, with the net result lowering the inharmonicity for the added diameter. Using the relationships of core to overall wrap diameter and the effects on tension, volume, and inharmonicity may help in the selection for the best fit of a universal string in a field repair. Step is the length of exposed underwrap or first layer wrap in a double wrapped string. Common step values are quarter, half, 3/4, and 1 inch. The ratio of diameter of overwrap wire to underwrap wire is generally 3:1. This ratio prevents the overwrap from settling into the grooves of the underwrap, which if it was only half the diameter. This means there's a pretty significant change to account for. The table shows how dramatically inharmonicity is affected by the step length. The greater the exposed difference, the greater the inharmonicity. The tension and volume calculations are affected so little by the step that it is not included in the calculations. That's why those numbers didn't change. Exposed core length is just like step. It's just another step, so the relationships all hold the same. Volume and tension calculations are affected so little that they're not even a part of the formula. Inharmonicity is dramatically affected by the exposed core length. This would indicate that, like a short step, the shortest possible exposed core seems ideal. Keep in mind two good reasons to have some exposed core, though. The whole string must have some clear room to displace during the actively producing the tone. If the wrap was right up to the bridge pin or agrafe, it would not vibrate well and reduce its sustain or would make a buzz. The other reason in scale alterations to leave enough room at the agrafe or V-bar end is to accommodate for elongation. Elongation is the amount of stretch the string will experience as it's brought up to and maintained at desired tension. What information does the string winder need to produce the bass string set we want? Core is pretty obvious, so is overall wrap diameter. It may be best to leave the final decision of wrap wire gauges up to the winder. Specifying the step on a double wrap string is a good thing. Loop to start of wrap is an important value, as is the length of wrap. A string winder will usually give plenty of core at the bitter end. Bitter means unfinished or raw end at the tuning pin in. Tolerances are very important in any specification. What will be the range of error from ideal, or on the practical side, from specified, that can be acceptable? You and your supplier need to know and agree on these terms. Another value that string manufacturers are requesting, and rightly so, is the hitch pin diameter. It's not a value that is used in any of the calculations and is thereby not required by the evaluation tools. It makes sense, though, that the closer fit, the better the tuning stability and general craftsmanship of the finished product. Another side note in specifying parameters to the string maker. Does the winder want the measurements with the string at rest or at tension? As a rebuilder, you need to have both measurements at hand. Normally, QA of the received strings will be at the rest condition. Values should be double-checked when the instrument is close to target pitch. Accuracy in collecting and recording of the original or as-found scale data directly affects the quality of the evaluation and final scale installed in the instrument. The terminology used in this discussion is in concert with ScaleMaster, Scale Evaluation Software Toolkit, and may need to be interpreted to fit the specific evaluation tools you may use. Speaking length, the distance from the bridge pin furthest from the hitch pin, for the string being measured to the edge of the A graph furthest from the tuning pin, or the bridge pin on the top bridge furthest from the tuning pin, or the center of the V bar or capodiastral bar. Simply put, the termination points. Bridge to loop, from the speaking length termination pin on the bridge to the hitch pin. Bridge to start of wrap, speaking length termination pin on the bridge to the start of wrap, start of the under wrap if double wound. V bar, this is the distance of the top termination point to the start of the wrap. These two values are the exposed core lengths, and of course core diameter and overall wrap diameter. When is the best time to get all this data, especially in the overstrung area? Perhaps during the destructive phase. That's when taking the old strings off. Yeah, you're committed at that point. It can be done solo, but it's far easier with a partner. This diagram shows the various measurement points. The terminology is used in the Scale Mastery Evaluations toolkit and should be easily translated to any other tool. The math models used are all from Dave Roberts' Calculating Technicians articles from the Piano Technicians Guild Journal from September 1979 to April 1981. Thank you for participating in this presentation. I hope you found some good takeaway stuff to apply to your next restringing test. Look for other presentations on the website at www.oppor-tune-ist.com. This is Mark Gallant, and this is a production of Opportunist Piano Service.